In this video, we will discuss some probability rules. By the end of this video, you should be able to use the general addition rule and the general multiplication rule to find probabilities. You should be able to find conditional probabilities, determine if two events are independent or not, and use tree diagrams to find probabilities. First, the general addition rule. Last chapter, we learned that when two events are disjoint or mutually exclusive, the probability that one or the other occurs is the sum of the probabilities of the two events. But we frequently have to find probabilities where the events are not disjoint. And here's an example. And I'll use this example to derive or come up with the general addition rule. So here's the question. A survey of college students found that 56% live in a campus residence hall, 62% participate in a campus meal program, and 42% do both. Okay? What is the probability that a randomly selected student either lives or eats on campus? Okay, so we know that these are not mutually exclusive or disjoint because there is a group of them that do both. Okay, so I have to deal with a situation where they're overlapping. Okay, now I'll consider this part of the Venn diagram those that live on campus. This side. And this part eat on campus. Okay, now of this, let me actually change the color here. Okay, in this circle, we find 56% of college students. And in this circle, we see 62% of college students. Now the problem is the fact that this intersection right here, where they're overlapping, which by the way is the 42% that do both, is being double counted. It's being counted both within the students that live on campus and the group that eat on campus. Okay, so the way that you find the probability that a randomly selected student either lives on campus or eats on campus, meaning I'm trying to find the intersection of them, I'd have to deal with this formula, okay, where I look at the probability of one plus the probability of the other minus the intersection, meaning the part they have in common, because that has been double counted. Okay, so using this formula, which is the general addition formula, I can find out that the probability that a student lives and eats, I'll say lives and, or eats, equals the probability that they live on campus plus the probability they eat on campus minus the probability that they do both. Okay, now for the sake of space, I'm going to leave that there and just erase and put in numbers. So the probability that they live on campus is 56%. Probability they eat on campus is 62%. And the probability they do both is 42%. Okay, so I simply add them together and then subtract. So 0.56 plus 0.62 minus 0.42 is 76%. 0.76 or 76% of students either live or eat on campus. Next, we will look at conditional probabilities. A conditional probability is where we look at a subset of the population and ask a probability question about that subset. Okay, so here is some data, a contingency table where it's 4th, 5th, and 6th graders were asked a series of questions, one of which is, what is your primary goal? Is it to get good grades? Is it to be popular? Or is it to do well in sports? Okay, and that's broken up also by gender of the student. Okay, now we can look at some questions about this data. And the first one we'll look at is girl intersect popular. This, again, symbol is the intersection. Okay, and it means and. So what is the probability that a student is a girl and their primary goal is to be popular? Okay, now girls are here and the goals are popular is here. And so I'm looking at this 91. So 91 girls want to be, or sorry, 91 students are both girls and want to be popular out of the total 478. Okay, now, because this bottom number is the total population, we are not looking at a conditional probability. Okay, now in the next two, we are looking at a conditional probability. Okay, and we have some new notation here that I want to point out in that this bar right here is read given. So, this is read the probability that someone is, their primary goal is sports, given that they are a girl. Okay, now this is what limits my population. So I'm looking just at girls, female students. Okay, now the probability that given that they're a female student, so out of the 251 female students, 30 of them, their primary focus, their primary goal is to do well in sports. Okay, now that changes if we are looking at the probability that someone is a girl, given that their primary goal is sports. Okay, in this one, we're looking just at sports. Okay, and of the 90 students who said their primary goal was to do well in sports, 30 of them were girls. Okay, those are two very different questions, even though they're both, you know, the same subset of girls who want to do well in sports of 30. The condition is different, and so the probability is different. So here is the formula for conditional probability, that the probability of B given A is equal to the probability of A intersect B divided by the probability of A. Okay, looking at this intersection where something is both A and B divided by how you're restricting the population. Next, let's look at independence. Last chapter, I gave the definition of independence as the result of two occurrences don't affect each other. And that's true, but it may not be the best working definition to test to see if two occurrences are independent or not. Okay, but now that we have the tool of conditional probability, we can come up with a mathematical definition for independence. And that is this one. The probability that B given A, again this means given A, is equal to, the probability of B given A is equal to the probability of B. Meaning that the probability that B will occur is independent of whether or not A has occurred or will occur. Okay, let's look at two questions with this same primary goal data. Are grades and gender independent? Well, we will look at the probability that grades are the primary goal given one of the genders. It doesn't matter which one you use. Okay, I will use girl just like in the last example. And see if that's equal to the probability that someone's primary goal is grades. Okay, and I compute this using this formula that we just talked about. And I will look at grades and girl. So grades and girl is 130 divided by girl, which is 251. Is that equal to or roughly equal to just grades? So grades will be grades. 247 divided by the total 478. Okay, now be a little bit forgiving with this data because we're dealing with real numbers. So if they're just really, really close, then that'll be good enough for us. 130 divided by 251 is about 0.518. And is that roughly equal to 274 divided by 478? 0.517. Okay. Now you may be saying mathematically they're not exactly the same, but we're dealing with real numbers here. Okay, so you have to be somewhat forgiving, and these are close enough to say that yeah, they probably are independent of each other from this data. Okay, so I would say yes, and we can say, are they independent? And I would say yes. Okay, next example. Next example, are sports and gender independent? Again, we will look at the probability of sports given gender, and I'll again pick girl, equal to question mark probability of sports. Okay, now sports given girl, I will look at sports and girl, so a girl and sports is the main primary goal, is 30. Out of girl, yes, is 251. Is that equal to sports out of everybody? 90 out of 478. Let's divide this to see if the decimals are close. 30 divided by 251 is 0.1195. Is that roughly equal to 90 divided by 478, which is 0.1883? Okay, I would say those are not really close together. Okay, so I would probably say no in this case. Those are not independent. One of the genders may be more inclined to focus on sports than the other. Okay. Now, I know this is kind of a gut feeling of, yeah, that's close and that's not close. We will come up with a more formal, even a more formal than this, rule of thumb to use much later on in the year. But for now, we'll look at just computing these conditional probabilities to figure out if they seem to be independent or not. Okay, the general multiplication rule. Last chapter, we learned that when two events are independent, the probability that A and B occurred is the probability of A times the probability of B, or A intersect B is equal to the probability of A times the probability of B. But we usually have to find probabilities where the events are not independent. Okay? And that also uses conditional probability. And here's the formula. The probability of A intersect B is equal to the probability of A times the probability of B given that A has occurred. Okay? Suppose we are asked this question. For men, binge drinking is defined as having 5 or more drinks in a row, and for women as having 4 or more drinks in a row. The difference is because of average difference in weight. According to a study by Harvard School of Public Health, 44% of college students engage in binge drinking. 37% drink moderately, and 19% abstain entirely. Another study published in the American Journal of Health Behavior finds that among binge drinkers aged 21 to 34, 17% have been involved in an alcohol-related automobile accident, while among non-bingers of the same age, only 9% have been involved in such accidents. Okay? Now, this is kind of like data overload. You're kind of trying to figure out how all these pieces fit together. Okay? And you're asked the question of, first, what is the probability that a randomly selected college student will be a binge drinker who has an alcohol-related car accident? And B, if there is an alcohol-related automobile accident, what is the probability that it was a binge drinker? Okay, now the way that we kind of organize all of this data is in what's called a tree diagram. I'm hoping that you can see, or will be able to see eventually, that we're really looking at, first of all, categorizing the data based on their drinking behavior. Okay, and then from there, we're given data based on their drinking behavior, whether or not they have been involved in an alcohol-related automobile accident. So that becomes my tree diagram. Okay, so starting off here, I'll move this down a little bit so I have some more space later. Okay, so these are my binge drinkers. These are moderate, and these are ones like me who abstain. Okay, of the binge drinkers, there's 0.44. Of those who drink moderately, 0.37, and those that abstain is 0.19. Okay, now of those who, let's see here, 17% of the binge drinkers have been involved in an automobile accident. So accident, no accident. Okay, 17%, which means that 83% have not been involved in an accident. I guess an alcohol-related car accident. Of those who drink moderately, 9%. Whoops, that's 0.9, not 9. And no accident is 0.91. And for those that abstain, they can't be in an alcohol-related car accident, at least cause one, because they don't drink. I'll say 0%, and no accident is 100%. Okay, so once I've organized this data, these questions become much more accessible. So what is the probability that a randomly selected college student will be a binge drinker who has had an alcohol-related car accident? So I'm looking at binge drinker who have had a car accident. Okay, I'm looking at that kind of part of the tree diagram and referring back to this formula. I will multiply those together. So as I move along my tree, I multiply. So I take 0.44 times 0.17, and I get 0.0748, or 7.48%. I'll move that actually up here just so I can organize it better. Okay, so 7.48% of college students are binge drinkers who have had an alcohol-related car accident. Okay, B, if there is an alcohol-related automobile accident, what is the probability that it was a binge drinker? Okay, now I'm looking at, this is a conditional probability looking at alcohol-related automobile accidents. Let me look at those. That's this kind and this kind, and I can look at this one too, but that'll be 0. So I just found that binge drinker who were in an alcohol-related automobile accident is 0.0748. And I can similarly find it for moderate drinkers as 0.37 times 0.09 and get that to be 0.0333. And if I multiply 0.19 times 0.00, I get 0. Okay, now I'm looking at out of these 3 cases, so I will add these up. And 0.0748 plus 0.0333, and I get 0.1081, and that is, I'm looking out of those accidents. The probability that they were a binge drinker is this number, 0.0748. 0.0748 divided by the 0.1081 that I just found, and I find that 69.2. So 69.2% is this one over here. I'll go over here. Okay, almost 70% chance that they are someone who engages in binge drinking. So this video was about some probability rules, about the general addition rule and the general multiplication rule. was about conditional probabilities and determining if two events are independent or not, and also using tree diagrams to answer some pretty complicated questions. Thank you so much for watching.